Hello everyone, I'm Sherry. Today I'm going to talk constructing the relative importance of species sorting and dispersal limitation in shaping marine bacterial versus protist communities. To hear, you may question about what is species sorting, or what is dispersal limitation, or even you may curious of are species sorting and dispersal limitation really do something in community assembly? Assembly means community distribution and composition. Thanks to greatly advanced microbial biogeography, some people say distance-decay relationship can solve this problem. So you must know what is distance-decay relationship. It describes how the similarity of a biological community decreases as the geographic distance increases. So once you have a further distance, then you will get a lower community similarity. That means if you get a closer distance, then the similarity is higher. So another question, what makes two closer places have a higher community similarity? I have to tell you, distance decay patterns suggest potential driving force underlying community assembly. And the two major forces. One is species sorting. It describes this community distribution and abundances related to the environmental or biotic conditions. And the other is dispersal limitation. It implies that not all suitable habitat can be occupied by species. It depends on the capacity to disperse to habitat. Let me explain it by a little story. When you zoom in this figure, we assume that there are three communities. And distance between community A, B, and AC are equal. But community A and community C have closer environmental factors. So the microbial prefer to go there. This means species sorting, they just go where they prefer to go. And on the other hand, there are three communities, and community A, B, the distance between A, B is closer than distance between AC. But no matter how the environmental factors are similar or not, the microbial can only swim to a closer place. This means dispersal limitation. It just depends on their capacity to disperse. So this is our aim, is to compare the relative importance of species sorting and dispersal limitation in structuring bacterial versus protist communities. So when we further know that, then we can further explore which hypothesis is more fit on our study. And one is size plasticity. It tells us smaller organisms are less environment filters than larger organisms. In our study, the smaller organisms means bacteria. And this means our community is more dominant by dispersal limitation. And the second is size dispersal. It tells us smaller organisms are more likely affected by species sorting than dispersal limitation. This means our community is more dominant by species sorting. Okay, so for sampling, we will first sampling for 11 days in East China Sea in August 2014, and 33 stations for total 74 water samples. And we will collect 3 water levels for surface, deep profile maximum, and bottom. And when you look to these figures, the circle means surface, the square means deep profile maximum, and star means bottom. And you will see the red and blue squares. That means their surface level and DCM levels are overlapping. Okay. For sample preparation, we will first get a 15-liter seawater, and then we filter it. Then we go to DNA extraction to get microbial DNA. Then we will do polymerase chain reactions, PCR, to amplify the DNA sequence. Then we will send it to the Illumina MiSeq platform to get the DNA sequence. And when the data sent back to us, then we will use our program to do the further analysis. Okay, so this is our data and some of the data, and I just cut it down by random. The reads means how many individuals we get, and OTU means these individuals can separate into how many groups. And one station means communities. Okay, so how did we study? To prove whether species sorting and dispersal limitation can really play the role in shaping community assembly, we'll first use distance decay relationship and use Reddy-Curtis similarity index to calculate it. Okay. The similarity equals 1 minus this similarity. When you gather higher similarity, when you get a higher number of this similarity, that means the beta diversity is lower. And in the other hand, when you get a lower number of this, that means your similarity is lower and your beta diversity is higher. And we will use distance-based redundancy analysis to see whether this is significant. And second, we will do variation partitioning. It tells us how many percentage can be explained by good factors. In our study, we separate it into two factors. One is environmental factors, and the other is spatial effect. Environmental factors means our study is the environment is more controlled by temperature, salinity, flow, or nutrient. And on the other hand, spatial effect means it's more controlled by distance or diffusion ability. And the region two circles are overlapping means either two factors can explain. Then we will get E without S, means pure environmental variation without a spatial component, means species sorting. And S without E, pure spatial variation without an environmental component, as dispersal limitation. Then we get species sorting to divide dispersal limitation. This is so-called sorting dispersal effect ratio. Why we use ratio? Because it can distinguish the dominance of species sorting and dispersal limitation in a relative sense. So if you get a higher ratio, that means your community is more dominant by species sorting. When you get a lower ratio, that means your community is more dominant by dispersal limitation. So this is a relative important way to see. Okay. And third, we will use new model analysis. It's just a statistical way, and it's the so-called one-way ANOVA. And the fourth, we will do habitat niche breeds. It's a crucial trait that influences the relative importance of species sorting and dispersal limitation affecting communities. And this is its formula. And we will do generalized linear mixed effect model, GLMM ANOVA, to test whether it is significant. And when you get a higher habitat niche breeds, it means the community is more governed by dispersal limitation. So what did we find? In these two pictures, you can see A is bacterial and B is protist. The x-axis is geographic distance and the y-axis is community similarity. And the three colors, red means surface, yellow means DCN, and blue means bottom. And when you use the redundancy analysis to test whether it is significant, we will see it is significant. So we will say the species sorting and dispersal limitation are really exist. It really do something in community assembly. And second, you can see this is the variation partitioning and new model analysis. And for x-axis, it's the clean water level. And for y-axis, it's sorting dispersal effect ratio. And for the square, it's bacterial communities. And triangle means protease community. In these two figures, you can see all of the triangle are higher than square. The protists are all higher than bacteria. This means protists were more governed by species sorting. And last, you see the half-damage breeds. In these three figures, one is A is surface, B is DCM, and C is bottom. In the x-axis, this is two communities. And for y-axis, it's half-damage breeds. And in these three figures, you can see all of the bacterial communities are higher than protease communities. This means bacterial communities are more governed by dispersal limitation. So finally, we get to discussion. We find lower sorting dispersal effect ratio for bacterial communities relative to protease communities in all three dots there. So this means protease communities were more governed by species sorting. And we also find bacterial communities are more governed by dispersal limitation. So this supports the size plasticity hypothesis. Smaller organisms are less environment filtered than larger organisms. Thank you.